Hey everyone, and welcome to this evening. Well, for me, this evening, today's second webinar brought to you from Exida. Just while I'm kind of chatting, anyone has any issues just with audio, maybe just type it in the questions. But we'll get stuck in. So today's webinar is on streamlining integration test plans during FMEA. My name is Paddy Healy, and thank you for joining us this evening. As always, with our webinars, the recording will be made available and a summary slide set will also be made available. So yeah, many never think of creating integration test objectives during an FMEA, but it really is the opportune time to do it while you're in the middle of doing your architecture design. That's the ideal time to design and develop your integration tests. As I say, as we go through this webinar, you'll kind of get an insight as to why. Generally, the earlier these type of analysis are done, the more engineering hours that can be saved, and then obviously that leads to making sure a project can come in under budget. So yeah, this is the fourth in the series, the fall or autumn series FMEAs. As I say, I will be doing this evenings next week as well, the FMEA to FMEDA process. And then the final one on the 1st of November will be brought to you by Dr. Molly O'Brien. So if you haven't already signed up, please do so. But as I said, all the webinars are always made available afterwards. So a little bit about Exida. The company was founded back in 2000 by several of the world's top reliability and safety experts, and professionals around the world turn to Exida for guidance based on that experience and knowledge when it comes to certification related industries for automation, functional safety, alarm management and cybersecurity. And as you can see, Exida has really grown in those 23 years to be a global company with offices dotted all across the world. So whatever time zone you're in, we've someone there that will be able to speak with you and help you in your functional safety journey. Exida, there's three main facets to the company. We have the system lifecycle services, we have the certification and assessment, which I am part of, and then also the engineering tools division. And I think something that's kind of unique with Exida in that regard is that the engineering tools division actually develop, and we have a software development team in-house, and they develop the tools that we use on a daily basis and that we also then make available to our customers. Two of those, Excellentia is one which you may be familiar with, which is a suite of applications. And then the one that I would use on a daily basis is OEMX. Again, this is a suite of applications comprised of RecX, which is for doing your requirements, entry and tracking, ArcX for FMEA, HAZOP, cyber threat analysis, and then FMEDAX, which it speaks for itself. It's for doing FMEDAs. And the core element within OEMX is our CRD, our Component Reliability Database. So a market report back from 2015 showed that Exida was the global leader in safety device certifications. And in the specific logic solver category, where the 4 certifications were done over 40 years ago, Exida has overcome that 20-year head start to become the leader in that particular category. As I said, there are many facets to Exida, and another key part to Exida is it's a knowledge base. It not only obviously provides a service to customers, but it also builds a knowledge, a library of information that is made available to customers. So whether that's books, white papers, these webinars, all this reference material is made available. And just one, as I said earlier, that I want to just bring your attention to is the CRD, the Component Reliability Database Handbook, which is available, but it's also now incorporated into our OEMX tool. So if you're in the product design field, functional safety, and you're looking for failure rates for components, this is the database for you, because whatever components you use in your design, you guarantee that it's in those handbooks. So just before we get into integration tests, just a kind of quick introduction as to what is failure mode and effect analysis. So I suppose by using a definition, failure mode means the ways or modes in which something might fail, and then what effect that failure has on your system. And the reason I'm kind of giving this little introduction is many people have different interpretations of what an FMEA is. So yeah, it's nice to just kind of get a very strict definition. Design FMEA is a very effective design verification technique. An FMEA is a systematic procedure designed to find problems and recommend mitigations in a design. And an entire system architecture is analyzed one block at a time at multiple levels. And just picking up on that last point, and speaking about architecture levels, it's something that we do at Exida, that the lower down a design you go in terms of the subsystem architecture, the more accurate your FMEA will be. And just to put that into context, if you're doing an FMEA and you describe deviations and mitigations at a system level, it's very hard to expect those deviations and mitigations to be accurate and applicable to a power supply and then also to a microcontroller. So the finer the resolution you go down in terms of your analysis, in terms of the blocks of your particular system, the better your FMEA will be, and that leads then to a much more accurate and better FMEDA. So what are the objectives for an FMEA? So find problems in the design, starting with high-level architecture, and as I say, work your way down through your system design, through each of the different subsystem blocks, until you get to the point where your block, the block you're looking at, has the same functional failure modes, and that's where you would stop. That's one particular block in your design, and then you move on to the next one. The next objective would be to recommend mitigations in the design. How can we fix the problem? Whether it's by introducing more diagnostics, redundancy, or maybe a change in your actual design. And that brings me back to what I said at the start. The earlier an FMEA is done, the better, because you can, before you actually start building your product, you can look at your design on paper and look to see how that will actually work in the real world. The next objective is to update requirements as mitigations are chosen. Then define integration tests, which is this evening's webinar. Provide inputs to the FMEDA. As I say, the more accurate your FMEA is, the better your FMEDA will be. And then document the design choices and train new staff members. And the ultimate reason or the end goal for all this is you can accomplish this with the minimum engineering hours, which means you will come in under budget, which is what everyone ultimately wants. So the next thing we're going to speak about is, obviously, when you're doing an FMEA, you'll have different people on the team and what roles they will take up. So you can have few different kind of examples here, but I suppose the main one we're going to speak about this evening is the test engineer, or someone on the team who has that kind of test engineering experience, that they have the ability to create integration and validation tests as need is discovered in the FMEA. So before we get into more detail on integration tests, we're just going to very quickly speak about fault injection testing, because sometimes we get customers and what's the difference between the two? Are they not the same? So just a quick kind of definition on fault injection testing. This is a method for verifying the effectiveness of fault tolerance mechanisms and determining how well a safety critical system can detect and respond to different types of faults. It involves intentionally introducing faults or errors into the system to evaluate its response. This testing helps ensure that safety critical systems can maintain a predefined level of safety even when faults occur. And then the difference is with integration testing, this is the phase in the development cycle where individual modules or blocks in your design are combined and tested together as a larger system. So you may have someone who's doing the power supply they've designed that power supply to a particular specification, and you have someone who's doing the logic part of the design. Now it's time to put those two parts of your system together and see how they work. And the primary objectives of integration testing are to verify, as I say, interface compatibility, ensure that your power supply has the correct voltages and currents for the rest of the system. The next one is to detect integration issues, identify and rectify any problems related to the integration of software components or modules, such as data incompatibilities. The next one then is to validate the overall system functionality. Next is to evaluate fault tolerance, and then finally to demonstrate compliance. So in practice, how does that look, and where does the different types of tests come into play? So when you're doing, you're starting out with your requirements and design tracking, what drives your design requirements? Is it market, regulatory requirements, risk analysis requirements, or a combination of all these? These are all fed into your design requirements. And then from your design requirements, you break that down into your safety requirements and non-safety requirements. And where we will jump from this now, as you can see here from our design requirements, we have our validation tests. And once you describe your validation tests, you need to link these to your safety requirements and non-safety requirements and tick them off as you go along. When you get further down into the detail of your system and looking at the architecture design, you are now looking at integration tests. And as I say, the further down into your design that you go, the lower the levels, and you have to describe and design integration tests. And we'll look at a more practical example in a few moments. So with integration tests, as I said, the tests are to confirm that multiple design units work together properly. Hardware with hardware, all the various different hardware elements in your design are all compatible, and they work well together, and there's no hidden surprises. Software components work with software components, programmable electronic hardware with software components, and then the overall system integration, looking at the holistic tying it all together, looking at your design as different pieces of a puzzle. Do they all link together correctly, and that you're not trying to smash them together to make them fit. So looking at integration test plans, the list of integration test objectives established during the architecture design, or FMEA, are reviewed for completeness. Any additional test objectives identified are added to the list. Tests should be written to confirm behavior in normal operation, and then also confirm the design behaves or fails as expected in abnormal operation. With a reviewed list of objectives, the test plans are completed by identifying the test environment, details including the person responsible, versions under test, any specific pass-fail criteria, and any test equipment needed. Results are often recorded on the test plan, and as I showed previously, this is where your integration tests link back to your design if you're using whatever type of tool you're using, where you can link different action items leading from your different tests and design levels. So we'll look at it now, another practical example of integration tests. We've drilled down in our design. We're looking at a power supply here, and we're looking at the lowest architecture level within that power supply. So as you can see, our 24-volt external power supply is now further broken down into 5 nodes, each with a different output or function within our particular product. So if we recall that integration tests confirm that multiple design units work together properly, what tests might make sense for node 1? So if we look at node 1, we have our 24-volt external power supply. Within our system, we have an EMC filter, an overvoltage diagnostics, overcurrent, and reverse polarity. So what integration tests might we describe to make sure that this part of our system works correctly? And I'll give everyone a few moments just to have a little think. So if we skip on, so possible integration tests that we might establish, and obviously you may have some yourself, and again this is all quite relevant to your particular design, your product that you're looking at. You might have different integration tests. But test one in our example here might be to set the voltage to 30 volts outside the tolerance of our system, and verify that the overvoltage diagnostic protected the power supply circuit. The next test might be to reverse the polarity of the input voltage and verify that the circuit protected node 1 or kept operating normally. Third test might be to put an artificial load on the circuit output and verify that the circuit protected itself. And then finally, we might put an RF signal generator on the input and verify that the circuit protected itself and the system continued to operate normally. And this is testing our EMC filter. So yeah, as I said, you may have thought of a few other ones in the list, or you may have some other ones specific to your particular design. So kind of looking at our architecture there and just thinking of that little practical example, what we'll now look at is how an integration test is put together practically in terms of your documentation. So depending on what tool you're using, or you may just be using Office or an Excel or something like that, but we're going to use ArcX here in our particular example. We're now going to look at our 12 volt power supply. We're looking at the sub-block within our overall power supply design, 12 volt power supply. This is our unit node editor within ArcX. So the next thing we want to do is we want to create a new test objective for our 12 volt power supply. So by clicking on this button here, we now have our 12 volt power supply, a blank test objective has now been created under this particular block in our design. If we now double click on this 12 volt power supply description here, what we now get is this next window that comes up, and this allows us to put in a lot more detail about our particular test. We give it a name, what type of test it is, whether it's a validation, integration, fault injection, or a software module test. We might give it a bit more of a description here. And I suppose one of the main important things to enter here are our expected results. So you as the designer, you should have an understanding and an expectation as to how this particular test will be carried out and what output you expect to see. So you put that in here in your expected results. What else you might add in here is you can add some reference documents, maybe schematics, or some other diagrams that are relevant to this particular test. And that's how we, using our OEMX tool, how we integrate test objectives into our flow, our document flow when we're doing our FMEA, FMEDA. So that concludes this evening's webinar. Nice little short one, but an important one all the same, in that, as I say, the main thing is to get across how important it is to do these type of things. Obviously your FMEA, FMEDA, but then within that, your integration tests, how important it is to describe them and design them as early as possible, because they save countless engineering hours. FMEAs are an effective design verification method that can detect design issues early in the development process. Many consider them to be the best possible technique to show compliance with functional safety standards. And they can also reduce rework, which reduces cost and time to market. As I said earlier, if you do your FMEA and FMEDA early on, before you've actually physically built the prototype, you may find a particular design flaw that will be easy to rectify digitally in your ECAD program, whether it's Altium, whatever program you're using, instead of actually getting to the point where you've manufactured a few prototypes. So not only now have you to go back and change your design digitally, but you also have to do another rerun of your PCBs. And then next generation FMEA tools have built-in FMEA failure modes per block type, known effective mitigations, and this leads to simplified entry. So just to reiterate, this is the fourth webinar in the fall-autumn series brought to you by Exida on FMEAs. Next week, I'll be going through FMEA to FMEDA process, and what we're getting from that is better results, less hours, which is everyone's goal, I suppose. And then on November 1st, Dr. Molly O'Brien will bring you a Streamline FMEA and doing a microcomputer example demo. So I'd like to thank everyone again for your time and attention this evening. Hopefully you found this informative. As I said at the start, Exida has a huge library of white papers and books and webinars which you can get on our YouTube channel and then also through our exida.com website. But yeah, please reach out to us. Always good to hear from customers or potential customers. So if you have anything you'd like to, any feedback, just reach out to us at info@exida.com. But in terms of tonight's webinar, if anyone has any questions, please, take this opportunity now to type them into the question box. As I say, depending on where you are in the world, you might be at the point where you kind of know, this is it, I'm done. My day is over. But look, I'll give everyone a few moments just, if any questions come to mind. But if you're looking back at any of the webinars, as I say, the email address is there. Reach out to us. We're always happy to link back to people and give as much information as we can. Now, as I said earlier, I think everyone is quiet today. As I say, you're probably just trying to either wrap up your day, or maybe, depending on where you are in the world, you're just getting your day started. So yeah, I think at that point we will call it an evening. Again, thank you for your time and attention, and look forward to seeing you back next week for the next in our webinar series. So thank you, everyone.